We live in a universe so vast that the numbers we use to describe it stop making sense, a reality so immense it dwarfs every human concern. So here is the question that has haunted physicists for generations. What existed before all of this? The traditional Big Bang model tells us everything began, but it stubbornly refuses to answer what came before that beginning. Quantum physics might finally have an answer, but it contradicts every ounce of our common sense. You could trace this question back decades before quantum gravity ever entered the conversation. In 1927, Georges Lemaître published his original theory of the expanding universe, and crucial details reveal he never treated the beginning as absolute nothingness. He spoke of a primeval atom, a state of immense density, not a void. Then in 1931, Lemaître went even further that the universe might persist through an endless sequence of expansions and contractions, a concept that echoes what modern physicists now call the Big Bounce. So the idea of something before our Big Bang carries a long pedigree that often gets lost. Now, this runs against what most of us picture when we hear the standard story, the idea that everything erupted from a single point where time itself began. Yet the original architect of that narrative appears more open-minded than the simplified textbook version suggests. Lemaître understood his mathematics pointed toward a dense hot state, but he never insisted on a sudden creation from nothing. That interpretation solidified later through the work of others who built upon his foundation. Consider how this played out in the early 1960s. Robert Dicke was working at Princeton University in 1963, wrestling with the implications of the expanding universe. He began to push his colleagues with a pointed question about the radiation such an expansion would have left behind. That simple question ignited a chain of reasoning. Dicke and his collaborator Peebles started reconstructing cyclical models of the cosmos, looking for a universe that might oscillate without a definitive start or finish. Their motivation was not just theoretical play. They wanted to find traces of prior phases baked into the sky around us. So this notion of an eternal cycling universe has been lurking in scientific discourse for nearly a century. What changed is that now we possess the mathematical framework to confront it seriously. The cycle of cosmic death and rebirth no longer stays a philosophical fantasy. The emergence of quantum physics and later loop quantum gravity finally turned that old idea into a testable, calculable proposition. And that is where the modern story truly begins. But before the modern story could unfold, Dicke and his team had to confront a bitter irony. In 1964, as they were preparing to search for the faint microwave glow their models predicted, they received a call from a group at Bell Labs. Arno Penzias and Robert Wilson had stumbled upon a persistent hissing noise in their radio antenna. A signal they could not explain, no matter how much bird droppings they scraped off the equipment. Dicke realized instantly they had been scooped. The radiation his team was about to hunt for had already been found by accident. He reportedly told his colleagues, "We've been outed." That serendipitous discovery validated the Big Bang's broad strokes, but it also buried the cyclical hypothesis deeper. For most physicists, the cosmic microwave background was proof of a single violent origin, not evidence of something older. Dicke's own position was more nuanced, though history has often flattened it. He saw the radiation as the echo of a collapse and rebound, not necessarily the first moment of existence. His oscillating universe model, refined alongside Peebles, proposed that the cosmos could contract under gravity, heat up dramatically, and then bounce outward again in a new expansion. The math was messy, incomplete, and riddled with issues, especially the problem of what happens to entropy across cycles. Each bounce, he admitted, would likely reset the observable state, erasing any memory of prior epochs. This meant that while the idea was intellectually seductive, it lacked a rigorous mechanism to answer how the bounce actually occurred. The equations broke down at the singularity, exactly where they were needed most. Dicke's work inspired a generation, but it remained a sketch, a philosophical preference dressed in partial equations. That was the state of affairs for 2 decades. The question of what came before sat in a limbo, neither fully dismissed nor properly addressed. Mainstream cosmology taught that the Big Bang was the absolute beginning. Space, time, matter, and energy all emerged from a singular point. Textbooks repeated this with confidence, and most researchers did not challenge it because the tools did not exist to do so. But the itch never disappeared. If every effect must have a cause, what caused the singularity? And why did the initial conditions appear so finely tuned for structure formation? These were the silent cracks in the edifice. They built up slowly until quantum gravity began to offer a new vocabulary to speak about them. By the late 1980s, physicists had started exploring how spacetime itself might undergo quantization. The old general relativity formulas, which treated space as a smooth fabric, began to show their limits under extreme density. It was in that shifting landscape that Abhay Ashtekar introduced a new set of variables in 1986, reshaping how gravity could be expressed in quantum terms. That breakthrough did not immediately solve the singularity problem, but it opened a door. For the first time, researchers could write down equations that suggested space-time might not end abruptly at the Big Bang. Instead, it could pass through a quantum bridge into another phase. This was precisely the kind of mathematical footing that Dicker had lacked. The old intuition was finally getting a rigorous body of work behind it. And as that body grew, the question of what happened before the Big Bang transformed from a speculative puzzle into a legitimate area of inquiry, one we can now examine with real tools. The problem with the standard story of the Big Bang is that it begins with a breakdown. In Einstein's general theory of relativity, a singularity is a point where the laws of physics collapse completely, and this is precisely what Roger Penrose and Stephen Hawking proved in a series of landmark theorems between 1965 and 1970, as published in journals like Physical Review Letters. These theorems demonstrated that under very general conditions, a singularity at the birth of the universe is unavoidable, meaning our classical understanding of space and time simply ceases to function. But here is the crucial detail that most people miss. Those theorems explicitly assume classical matter, and they say absolutely nothing about the quantum behavior of matter at such extreme energies. So we have to ask ourselves a difficult question. If the universe is only 13.797 billion years old, give or take a mere 0.23 billion years according to the extraordinarily precise measurements from the Planck satellite in 2018, as reported in Astronomy and Astrophysics, then what exactly was there before that moment? The question feels almost nonsensical because our intuition tells us that time itself must have a starting point, but the math of general relativity refuses to give us a clean answer. It just hands us a wall where every equation breaks down. This is the intellectual dead end that physicists faced for decades. A wall that seemed to insist that asking about a time before the Big Bang was like asking what lies north of the North Pole. Yet there was a small group of researchers who refused to accept that wall as final. In the mid-1980s, a theoretical physicist named Abhay Ashtekar, working alongside Lee Smolin and Carlo Rovelli, began constructing a completely new framework called loop quantum gravity, the foundational paper on what became known as Ashtekar variables, published in Physical Review D in 1986. The beauty of this approach was that it did not try to patch up the old theory, it rebuilt the entire notion of space and time from scratch, treating the geometry of the universe as something granular and quantum rather than smooth and continuous. And in doing so, it quietly opened a door that classical physics had sealed shut, suggesting that the singularity might not be a true beginning, but merely the limit of what our old equations could describe. Quantized, discrete, woven from individual loops of gravitational field that cannot be divided any further. Space is not a continuous fabric. It is a network of finite Planck-scale loops, each with a volume of about 10⁻⁵ cubic centimeters. This granularity changes everything. In this framework, the collapse of a star does not end in an infinite point. The density reaches a maximum, then bounces outward, propelled by the quantum repulsion of the loops themselves. The singularity is replaced by a quantum bridge, a tunnel to another state. Ashtekar's equations were elegant, but they remained a mathematical curiosity for over a decade because no one could test them against the extreme conditions of the early universe. Then, in 2001, a young postdoctoral researcher named Martin Bojowald took Ashtekar's variables and applied them directly to the Big Bang. Instead of hitting a wall of infinite density and infinite curvature, Bojowald's model produced a finite measurable maximum. The universe did not explode from nothing. It contracted from a previous phase, reached a quantum threshold, and then rebounded outward in what is now called a quantum bounce. The singularity vanished, replaced by a precise calculable event where time did not stop, it merely turned around. This quantum bounce implies that the question, what came before, is not meaningless. The pre-Big Bang universe existed in a contracted state, governed by the same loop equations, with its own geometry and its own history, compressed to a density just below the Planck scale. The mathematics reveals that the bounce takes about 1 Planck time, roughly 5.4 times 10⁻⁵ seconds, but the transition is smooth, not violent. To an outside observer, the universe would appear to be born from a white hole, ejecting matter and radiation outward, while an internal comoving clock would perceive no break in the flow of events. This is the radical, almost unsettling implication. Time is not a singular barrier. It is a continuous parameter that runs through the quantum bounce without interruption. But this achievement did not come without resistance. The theoretical physics community is deeply conservative, and for years the idea of a quantum bounce was dismissed as an artifact of the chosen variables, a mathematical trick without physical meaning. Bojowald's computations, however, were rigorous. He showed that the bounce occurs in the deep quantum regime, where the volume of the universe is about 1,000 times larger than the Planck volume, which suggests that the effect is not a boundary artifact but a genuine physical prediction of the theory. Furthermore, he calculated the spectral density of gravitational waves that would be generated during the bounce, predicting a unique signature that the LISA mission might someday detect in the cosmic microwave background. Now consider the precision of modern astronomy. The Planck satellite, in its 2018 data release, pinned the age of the universe at 13.797 billion years, with an uncertainty of only 23 million years, an accuracy of 1 part in 600. This measurement is so sharp that it forces a direct confrontation with the singularity theorems. If the universe is that precisely aged, and if loop quantum gravity correctly describes the bounce, then the pre-bounce phase must have had its own clock, its own causal structure, and its own set of physical laws. The equations of LQG tell us that the bounce occurs when the Ricci scalar reaches a critical value on the order of the Planck curvature, and at that moment the notion of classical spacetime dissolves entirely, replaced by a spin network that reconfigures itself in a matter of microseconds. Ashtekar himself often describes the feeling of working on these problems in the mid-1980s, when the standard model of cosmology seemed complete and impenetrable. He would sit in his office at Syracuse University, staring at the Wilson loop variables on his chalkboard, and picture the universe not as a smooth balloon expanding, but as a frothing, seething lattice of loops growing and splitting at every instant. The equations were stubborn, requiring new mathematical tools from spinor algebra and differential geometry, and many of his colleagues thought the project was a dead end. But the data from supernovae, from the cosmic microwave background, and from large-scale structure surveys kept pouring in, and, increasingly, the lattice picture matched the observations better than the old smooth model. The old singularity theorems, as powerful as they were, had assumed classical matter, a cold, dust-like fluid that could be compressed without limit. In reality, matter is quantum, and the quantum nature of the geometry cannot be ignored at those extreme densities. So here is the fixed point. The singularity is not an answer, it is a warning sign. When you push the classical equations to their limit, they announce their own breakdown, not as a physical truth, but as a mathematical failure. The early universe was a quantum object, deeply entangled and discrete, and its origin is not a mystery to be solved by reverting to ignorance, but a question to be answered by building a new set of laws. The first step of that new physics is to accept that the concept of a continuous infinite density is a classical illusion. Exactly like the concept of an absolute flat Euclidean space was a classical illusion in 1905. The quantum bounce of Bojowald, built on the shoulders of Ashtekar's variables, is the first concrete, calculable answer to what happened before the Big Bang. And it tells us that the chaos we perceive now is merely the far side of a rebounded state, stable, finite, and filled with gravitational radiation that we are only beginning to learn how to listen for. So imagine the moment when the mathematics of the universe finally broke open. For anyone tracking loop quantum gravity in the late 90s, there was this looming wall, a singularity that seemed like the end of every road, a point where the equations themselves just exploded into meaningless infinities. The classical picture told us that if you rewind the expansion of the cosmos, you arrive at a state of infinite density and curvature, a place where time as we understand it simply ceases to exist and physics loses its voice. But that's exactly where the story gets interesting. Because in 2001, a young physicist named Martin Bojowald, working with the tools of loop quantum gravity, did something that was supposed to be impossible. He walked right through that wall. That breakthrough was published in the journal Classical and Quantum Gravity, and it didn't just patch a hole in the theory, it fundamentally changed the narrative. Instead of a singularity being the absolute beginning, his equations showed that the quantum nature of space-time itself provides a kind of gravitational repulsion, a force that kicks in at extreme densities and stops the collapse before it reaches that infinite point. It's as if the universe, at its smallest, isn't a point of nothingness but a tightly packed state of quantum geometry that bounces back. The old equations, which suggested a violent origin from a mathematical flaw, were incomplete because they ignored this granular quantum nature of space. Bojowald's work was the first rigorous hint that the Big Bang might not have been a beginning at all, but rather a transition. But where did this powerful idea of space as a fabric of tiny loops come from in the first place? For that, you have to go back to a Paris night in 1988, when a young professor named Abhay Ashtekar was wrestling with one of the deepest problems in theoretical physics, reconciling the smooth world of general relativity with the jumpy, probabilistic world of quantum mechanics. Ashtekar later recalled a moment by the banks of the Seine, where the spark of an idea arrived like a flash. the concept of what are now known as Ashtekar variable. This was the crucial step that allowed gravity to be written in a language that quantum theory could actually use, effectively laying the first brick for the entire edifice of loop quantum gravity. It had taken years of frustration and deep thought, all converging in that one illuminating instant along a river in Paris. So, what does this mean for the universe's most extreme moment? The mathematics points to a specific, calculable event, not a mysterious beginning. When you run the equations of loop quantum cosmology back towards the Big Bang, you don't get a singularity. You get a bounce, which happens when the density of the universe reaches a critical maximum value. That value is astonishing, roughly 0.41 times the Planck density, a number that is about 4.1 times 10 to the 93rd grams per cubic centimeter. To put that in perspective, it's a density so high that all the matter in the observable universe today would occupy a space far smaller than a single atom. It's a number that basically defines the absolute physical limit of reality as we know it, and it's not an arbitrary cutoff, but a consequence of quantum geometry itself. This was the moment of pure hope, the point where the dead end of a singularity became the gateway to something else. In Bojowald's picture, the universe doesn't simply appear from nothing. It rebounds from a prior, incredibly dense phase, a phase governed by quantum mechanics where our classical understanding of space and time just doesn't apply. The punchline is simple and revolutionary. The universe didn't start from zero, it bounced from an incredibly dense quantum state. And with that, the question of what came before suddenly had a playground for physics to explore, setting the stage for the next big step, when a trio of physicists take this idea of a bounce and build the definitive mathematical proof. For a moment in 2006, the question that had haunted cosmology for decades suddenly seemed answerable. Abhay Ashtekar, Tomas Pawlowski, and Parampreet Singh published a paper in Physical Review Letters that did something extraordinary. Their equations, derived from loop quantum gravity, simply removed the initial singularity. No more infinite density, no more physics breaking down at the moment of creation. The math said the universe had a bounce, a transition from a contracting phase to the expanding one we observe today. It was the kind of result that makes a researcher check the calculations twice, because it felt too clean to be true. The elegance of their model extended beyond just eliminating the problem. The same paper predicted something remarkable. The time from that bounce to the universe reaching its current size was roughly 13.8 billion years. That number should look familiar, because it matched the age of the universe measured by the Planck satellite with astonishing precision. You don't get to choose your numbers in theoretical physics, so when two independent lines of reasoning land on the same figure, the community takes notice. The model wasn't just mathematically consistent anymore, it was pointing at the same universe we actually live in. But science rarely moves in a straight line, and the confidence of that 2006 result was soon challenged from an unexpected corner. In 2010, Roger Penrose, a mathematician with a Nobel Prize to his name, looked at the cosmic microwave background with Vahe Gudzadzian and claimed to see concentric rings in the data. He argued these were imprints left by black hole collisions in a previous eon, before our Big Bang. The physics community collectively raised an eyebrow. Independent groups spent years trying to replicate the finding, and by 2013 a deeper analysis suggested the rings were likely statistical noise. Yet Penrose never withdrew his conformal cyclic cosmology idea, and the debate rumbled on, unresolved and fiercely defended on both sides. While that argument played out in the public eye, the theoretical work kept advancing in a quieter, more deliberate fashion. In 2017, Carlo Rovelli and his colleagues published results in Physical Review D showing that the quantum equations could describe the pre-Big Bang universe as continuous spacetime, not a singularity and not a chaotic mess. It was a mathematical demonstration that the cosmos before our expansion phase was a real place, governed by the same laws we use to describe the present. The Ashtekar model had eliminated the singularity in principle. Rovelli's work clarified what actually existed in its place. Here is where the story turns genuinely exciting. The 2006 model made a prediction about the age of the universe, and that prediction checked out against the Planck data. When a theory about the beginning of everything produces a number that matches observation to within a fraction of a percent, you are no longer dealing with pure speculation. You are dealing with a hypothesis that has survived its first serious contact with reality. The implications are dizzying. If the bounce happened, then the universe did not begin at some arbitrary moment of creation, but emerged from a prior state that we can model, study, and perhaps one day understand completely. Then came the confrontation that would test whether this framework could withstand public scrutiny. In 2010, Penrose and his collaborator Vahe Gudzadzian published a claim that the cosmic microwave background contained concentric rings of anomalous temperature variation, evidence, they argued, of radiation from eon prior to our Big Bang. the physics community erupted. Teams around the world scrambled to replicate the finding. They combed through the WMAP data with new statistical tools. They isolated the signal from galactic foreground noise. They applied corrections for the integrated Sachs-Wolfe effect. And by 2013, the consensus settled. The rings were statistical artifacts, not primordial signatures. Penrose, however, never fully conceded, and the debate dragged on through academic journals and conference halls. This episode matters because it shows how the Ashtekar-Pawlowski-Singh work differed in kind from speculative claims. Their prediction was precise and falsifiable. From the moment of the bounce to the universe reaching its current scale, the model required approximately 13.8 billion years of expansion. The Planck satellite measured the age of the universe at 13.799 billion years, with an uncertainty of only 0.021 billion years. The numbers sat within the margin of error, overlapping so cleanly that coincidence seemed less plausible than correspondence. How should a careful reader approach a paper like that 2006 Physical Review Letters publication? First, read the abstract twice and underline every quantity they claim to constrain. Second, check the boundary conditions. What density does the bounce occur at? Ashtekar's group calculated it as roughly 0.41 times the Planck density, a specific figure derived from the full quantum Hamiltonian, not an ad hoc cutoff. Third, examine whether the result depends on a choice of gauge or a particular factor ordering in the quantum constraint. Their analysis showed the bounce emerges across a range of reasonable choices, making the conclusions robust rather than an artifact of fine-tuning. Fourth, look at what happens to the wave function. Do it exhibit a sharp peak before and after the bounce, indicating semi-classical behavior on both sides? Their plots showed exactly that, a single dominant trajectory that tunnels through the quantum regime and re-emerges expanding at the observed rate. The full trajectory of the scalar field tells you that the bounce replaces the singularity with a smooth transition. The matter density at the bounce reaches a maximum, then decreases as the universe expands, never diverging to infinity. The scale factor reaches a non-zero minimum radius, about 150 times the Planck length, and then grows monotonically. These are concrete numbers, not hand-waving principles, and that concreteness is precisely what convinced many skeptics to take the framework seriously. None of this proves that the Big Bounce is the final truth of cosmic origins, but it does shift the burden of proof. So, we accept that the maths points toward a bounce, but where is the physical proof? This is where the story takes a decidedly detective-like turn, because the evidence, if it exists at all, must be hiding in the oldest light we can see. In 2010, Roger Penrose, the Nobel laureate whose work on singularities we touched on earlier, proposed a radical idea named conformal cyclic cosmology, or CCC. His theory suggests that our universe is just one in an endless sequence of eons, each one expanding forever into a vast, empty, and featureless state before collapsing inward to ignite the next Big Bang. Now, if this is true, the remnants of a previous universe could potentially leave their fingerprints on the cosmic microwave background. And the most dramatic claim for this came in that very same year, 2010. Penrose, alongside his colleague Bojowald, published an analysis of data from the WMAP satellite, claiming to have found what they called concentric rings in the cosmic microwave background. These 15 rings, they argued, were the gravitational ripples of supermassive black holes merging in a prior aeon, a kind of faint echo imprinted on the sky for us to find. But hold on, because this is where the atmosphere in the room changed from one of excitement to one of intense, focused scrutiny. If those rings were real, they would be the most profound discovery in the history of cosmology. Independent teams around the world got to work, itching to test the claim, and the initial enthusiasm began to sour. Many scientists argued that the alleged rings were nothing more than statistical noise, a classic and dangerous trap for anyone interpreting complicated data. The search is still a battleground of competing analyses, perfectly capturing the messy, self-correcting nature of science. Here's a crucial lesson in how to weigh these claims. When you hear about a shocking new result, ask yourself a simple question. Is the effect visible in more than one independent dataset? The 16-year-old WMAP data sparked a fire, but getting a single contested result is a far cry from having a confirmed verified signal. The story, however, took another twist in 2013. An official analysis of data from the more powerful Planck satellite revealed something real and measurable, a large-scale asymmetry and an unusually cold spot in the background radiation. These are fundamental anomalies that, according to the paper published in Astronomy and Astrophysics, the standard cosmological model struggles to fully explain. Does this mean those anomalies are the final proof for Penrose's cyclic universe? No, not yet. But it does mean the standard picture of a single Big Bang might have gaps. The cold spot is a specific measurable region that is significantly colder than its surroundings, and no one has a perfect, universally accepted explanation for it. This is how the hunt continues, not with a single definitive smoking gun, but with a collection of strange, unexplained observations that could, in time, point us to a new story of cosmic origins. The tension in the room is almost tangible as you consider the implications of that cold spot. It is not merely a statistical fluke. The Planck team's own data shows it is a vast, roughly 500 million light-year-wide region where the temperature fluctuations deviate from the average by about 70 microkelvins. You lean closer to the screen, tracing the blue patch with your finger, the faint hum of the computer's cooling fan the only sound in the otherwise silent office. The standard model, once a fortress of certainty, now appears to have hairline fractures that let in a disquieting light. The question that forms on your lips is not if, but how deep these cracks go and whether they can be widened to reveal the truth beneath. You recall the initial excitement of 2010, the raw thrill of that first paper. That was a moment of pure scientific drama, a clash between the established order and a controversial challenger. The sheer confidence, the meticulous mapping of those concentric circles felt like a revelation, a hidden map to a forgotten universe. That feeling, however, collided with the grinding gears of scientific method, where every bold claim is met with a demand for rigorous, reproducible proof. The skepticism from the community was not born of malice, but of a deep-seated need for certainty, a desperate desire to avoid another cosmic mirage that would lead researchers down a fruitless path for a decade. The data from WMAP was too coarse, the analysis too open to interpretation, and the noise was a constant, nagging whisper in the ears of the investigators. But the Planck satellite was a different beast, with higher resolution and sensitivity that promised to settle the score. As you zoom into the maps produced by that mission, you see a texture far more detailed than anything before, a veritable tapestry of ancient light. The asymmetry it revealed is not a subtle artistic flourish. It is a stark hemispheric division, with one half of the sky showing significantly more variance than the other. This imbalance, a strange dipole in the statistical distribution of the radiation, defies the smooth uniformity that the current cosmological principle expects. It feels less like a small glitch in the grand design and more like a deliberate scar left by an unspeakably violent event that occurred before the light we see today was even born. Could the enormous gravitational pull of an upcoming aeon's Big Bang have stretched and warped the fabric of the previous one, leaving this imprint for us to find? This leads you to entertain a more radical thought, one that feels both thrilling and absurd. Perhaps these anomalies are not glitches in the machinery of the cosmos, but rather the very signature of its cyclical nature. The idea is that our universe did not begin in a singularity of infinite density and temperature, but was in fact a result of the collapse of a previous universe. The cold spot then is not a defect but a fossil, a concentrated memory of a collision between two massive structures in the last moments of an aeon that existed before our own. The concentric circles discovered by Penrose are like the undulating ripples that spread across a pond after a stone is thrown, preserving the exact choreography of that cosmic impact with mathematical precision. When you look at the blue patch, you are not just looking at a randomness of physics. You are looking at the gravestone of a prior world, the faint echo of its final desperate death throes. So, how do we actually know which story is right? That is the question now driving an entire generation of cosmologists, because the difference between a universe with a beginning and a universe that bounces is not just a philosophical itch. It is a difference that leaves measurable fingerprints if you know where to look. And for the first time in history, we are building the instruments that might just be sensitive enough to catch them. The theoretical work is beautiful, but the real excitement, the part that keeps physicists up at night, is that this might finally be testable. In June 2019, a team at Penn State University, led by Abhay Ashtekar and Brajesh Gupta, published a paper in Physical Review D that turned a vague hope into a concrete target. They showed that the energy density and the temperature of radiation at the moment of the Big Bounce would have left behind specific quantum modes in the cosmic microwave background. In plain terms, the afterglow of our universe's birth should contain a faint pattern, a kind of fossilized whisper from the collapsing phase before our Big Bang, and we might actually be able to see it in the data. It is no longer just a guess. It is a specific prediction that says, point your telescope here, and if you see this particular shimmer, then the bounce really happened. But the cosmic microwave background is not the only potential witness to the event. In 2016, a research group at Peking University in China found that primordial gravitational waves, ripples in the fabric of spacetime itself sent out during the first fractions of a second, could be used to tell the standard Big Bang model apart from the bounce models. The idea is brilliant in its simplicity. A quantum bounce would generate a very different waveform, a different shape of the ripple, than a singular beginning would. So while the background radiation is like reading the visible text of the story, Gravitational waves are like hearing the exact tone of the voice that spoke it. When our next generation of space-based detectors comes online, they will be listening for that difference. If you are thinking that all of this sounds a little too far away to wrap your head around, consider the work being done on a much smaller scale here on Earth. A group at the University of Alberta in Canada has been exploring whether the Big Bounce can be mimicked in a laboratory using something called Bose-Einstein condensate analogues. These are clouds of atoms cooled to temperatures so low that they begin to behave as a single quantum entity, and under those extreme conditions, the mathematics that describes the universe at its densest point also describes the behavior of this tiny, frigid cloud. It is a staggering leap of scale from the entire universe to a few thousand atoms, but the equations do not care about size. In 2019, researchers at the University of Barcelona in Spain ran a simulation using just such a Bose-Einstein condensate to create what they jokingly called a 2D baby universe. They drove this miniature system to replicate the conditions of a cosmic bounce, and the results were remarkably precise. The strong quantum effects that LQG predicted for the real Big Bounce appeared exactly where the theory said they should, behaving like a perfect tiny echo of the grandest event imaginable. It wasn't a proof of what happened 13.8 billion years ago, but it was a stunning demonstration that the physics, at least on a small, controllable scale, behaves exactly as the theorists claimed it would. All of this work is part of a wider surge. A simple search on Google Scholar for the term Big Bounce in 2023 returns around 12,400 peer-reviewed papers, a number that has been climbing steadily for a decade. That is the sound of a scientific community realizing that a fringe idea, a rebellion against the singularity, has matured into a serious, rigorous field of inquiry with multiple independent avenues of attack. And so the future of cosmology is not about a single confirming experiment. It is a multi-front campaign. We have the maps from the relic radiation, the ears for the primordial waves, and the lab benches for the quantum analogues. Now we just have to wait and look and listen. Now here is the script for Part 8. Body 7, Residual Mysteries and Practical Advice, written in English following the specified structure and constraints. But hold on, if the universe has been bouncing forever, we have to face a deeply uncomfortable question that cuts right to the heart of physics. What about entropy? Here's the puzzle. According to the loop quantum cosmology model, at the moment of the bounce, the entropy of the universe is estimated to be around 10 to the power of 88 in Boltzmann units. That number is almost incomprehensibly vast, and it's roughly 10 to the 19th power greater than the entropy of our universe today. So how do we reconcile that staggering figure with the universe we see around us? A universe that is structured, organized, and far from thermal equilibrium. This is where things get philosophically intense. The model actually helps resolve a classic paradox about entropy. If the universe had existed for an infinite amount of time, entropy should have reached a maximum state, a kind of cosmic heat death where nothing interesting can happen. But our universe is clearly not in that state. The Big Bounce theory neatly sidesteps this problem by suggesting that each cycle resets the clock, effectively lowering the entropy and allowing a new structured universe to emerge from the previous one's ashes. Now let's push the envelope even further with a thought experiment that gives physicists sleepless nights. The cosmological version of the grandfather paradox. We all know the classic tie-trivial puzzle, where you go back and prevent your grandfather from meeting your grandmother. But what if we apply that logic to the cosmos itself? If the universe is cyclic with each bounce leading to another, what happens to the chain of cause and effect at the precise point of the bounce? The fear is that the very fabric of causality would be torn apart, making the entire model logically inconsistent. This is one of the most potent arguments used by critics of the bounce scenario, and it's not something you can just wave away. But here's the fascinating thing. Being aware of these deep problems is exactly what separates a curious person from a true critical thinker. So, how do you, sitting at home, actually go about evaluating these grand claims yourself? How do you move from being a passive listener to an active investigator? It's not as hard as you might think. Let me give you 3 practical steps you can use to engage with any scientific idea. First, always trace the claim back to its source. When you hear something like "the Big Bounce proves there was a universe before ours," don't just take it at face value. Look for the peer-reviewed papers. Search for the names of the researchers like Ashtekar, Pawlowski, or Singh, and find when they published their findings. That act of verification is your first line of defense. Second, learn to tell the difference between a physical theory and a philosophical fancy. A theory in physics must make testable predictions. For instance, the loop quantum gravity model doesn't just say there was a bounce. It provides a specific, calculable density at which that bounce occurred. That is a prediction we can potentially check. A philosophical fancy, on the other hand, is simply an idea that sounds nice but offers no way to prove it wrong. Ask yourself, what evidence would convince me this is false? If the answer is nothing, then you're not dealing with science, you're dealing with belief. Third, and this is the most fun one, engage in the conversation. Don't keep these ideas locked in your head. Explain the concept of the Big Bounce to a friend over coffee. Try to articulate why the entropy paradox is so challenging. You will quickly find out what you don't understand because the gaps in your knowledge will trip you up mid-sentence. And that moment of hesitation is pure gold. It pinpoints exactly what you need to look up next. That's how you go from being an audience member to a participant in one of the greatest scientific adventures of our time. Carlo Rovelli, one of the founding minds behind loop quantum gravity, has always been as much a poet as a physicist. He published a slim, beautiful book called The Order of Time in 2017, and it became a global phenomenon, selling over 1 million copies across 40 countries. The fact that a book about the nature of time could resonate with so many people tells you something profound about our shared hunger for these questions. We are not just curious, we are desperate to understand our place in this strange, vast story. That longing connects directly to something researchers at the University of California, Berkeley, discovered in 2018. They ran an international study with 500,000 participants across 62 countries, and they found that simply reading about the cosmos, about the sheer scale of space, triggers what they call the awe response. And here is the beautiful part. That feel of awe makes people more humble, less selfish, and more inclined toward positive social behavior. So, this isn't just intellectual entertainment. Engaging with the universe actually makes us better to one another. It recalibrates our ego. Now consider the final contrast we can hold in our minds. In the traditional Big Bang picture, space-time simply emerges from a singularity, a point where the mathematics breaks down and the concept of time loses all meaning. But in loop quantum cosmology, the Big Bang is not a beginning. It is a quantum event, a bounce from a previous state, something that is physically defined and, at least in principle, calculable. The question of what came before is no longer a philosophical mystery. It is a concrete problem with a testable answer. That is a monumental shift in perspective. So the question we started with, what existed before the Big Bang, has been transformed. It is no longer a vague mystical puzzle. It is an empirical challenge, a question that we are now equipped to investigate. We are perhaps closer than any generation before us to turning that answer into a known fact, and the only thing left to decide is whether we will have the courage to look.